Have you ever stood at an airport gate just staring at a massive jumbo jet and thought to yourself, how in the world does that work? I mean, it's a metal tube that weighs hundreds of tons. It seems like it should defy every law of physics just by existing, let alone flying. But it's not magic. It's actually an incredible, high-stakes dance of physics. So yeah, that's the big question, right? How does that 400-ton machine just hang out in the sky? Well, today, we're going to break down exactly how these incredible machines conquer gravity, piece by piece. Let's get into it. You see, the secret to flight isn't just one thing. It's actually a constant, dynamic battle, a tug-of-war, really, between four fundamental forces. And if you can understand this battle, you can understand flight. And here are our four competitors. You've got lift pushing up, and its direct opponent, weight, pulling down. Then you have thrust pushing the plane forward, fighting against drag, which is always trying to pull it backward. It's a perfect set of opposing pairs. For that plane to just cruise along nice and steady, all four of these forces have to be in perfect balance. Okay, so let's tackle the first big problem. I mean, the most obvious one, right? Overcoming gravity. How do you even get a massive machine like that off the ground? Well, our first opponent is weight. It's that relentless, non-stop pull of gravity trying to keep everything on the ground. And we're talking about everything. The plane itself, all the fuel, every passenger, every single suitcase. And get this, as the plane burns fuel, its weight is constantly changing. So the pilot is always making tiny adjustments. And the hero that fights against weight? That's lift. Lift is the amazing upward force that's generated when the wings move through the air. Now, to fly, lift has to equal weight, but to actually climb, lift has to be greater than weight. So how on earth does a simple wing create such a powerful force? Well, that question gets us right into the middle of a huge debate in aerodynamics. It's kind of like a physics showdown. In one corner, you've got Bernoulli's principle. The idea here is that because of the wing's curved shape, air flows faster over the top, creating lower pressure, which basically sucks the wing upwards. And in the other corner, you have good old Newton's third law. For every action, there's an equal and opposite reaction. The wing pushes air down, so the air pushes the wing up. So who's right? Surprise, they both are. NASA puts it best, saying they're really just two different ways of explaining the exact same thing. That pressure difference that Bernoulli talks about is what causes the air to get pushed down. And that downward pushed air is what creates the upward reaction force that Newton describes. They're two sides of the very same aerodynamic coin. You can't have one without the other. Okay, time for a quick myth bust. You might have learned this in school. I know I did. It's called the equal transit time theory. It says that a particle of air that splits at the front of the wing has to meet its buddy at the back at the same time. Well, NASA says that's totally wrong. In reality, the air screaming over the top of the wing gets to the back way before the air underneath. The real physics is just a lot cooler and more complex. So, what's the really crucial part here? Pilots in the cockpit aren't thinking about Bernoulli or Newton. What they actually control is something called the angle of attack, or AOA. It's just the angle the wing makes with the oncoming air. When a pilot pulls back on the controls, the nose pitches up, that angle of attack increases, and the wing generates more lift. But only up to a point. And that point is absolutely critical. If you increase the angle of attack too much, the smooth airflow just gives up. It separates from the top of the wing, becomes chaotic, and lift disappears almost instantly. That's called a stall. And here's the key takeaway. A stall has nothing to do with speed. It's all about exceeding that critical angle of attack. All right, so we've beaten gravity. We are off the ground. Awesome. But now we have a new problem. As we move forward, the air itself pushes back. It's time to tackle our second challenge, overcoming drag. And that pushback is called drag. It's the universe's way of saying not so fast. It's basically aerodynamic friction, always trying to slow the plane down. You know that feeling when you stick your hand out of a moving car window and the wind pushes it back? Yep, that's drag. Now, what's really interesting is that drag isn't just one simple force. We can break it down into two main types. Parasite drag is from the plane's shape and skin friction. It gets way worse the faster you go. But then there's induced drag, which is an unavoidable side effect of making lift. And here's the weird part. Induced drag is at its worst at low speeds, when the angle of attack is high. So how do you fight back against this constant, annoying drag? With one word, thrust. This is the raw power, the forward push from the engines. If you want to speed up, thrust has to be greater than drag. And if you want to cruise at a nice, constant speed, thrust has to exactly equal drag. So how does a jet engine actually make all that thrust? Well, you can boil it down to a super simple 4-step recipe. Suck, squeeze, bang, blow. First, the engine sucks in a massive amount of air. Then powerful fans squeeze that air down. Then you add fuel and ignite it. That's the bang. And finally, all that hot gas blows out the back at insane speeds. It's Newton's third law all over again. That huge action of gas going backward creates an equal and opposite reaction, pushing the plane forward. Okay, so we've got the forces to get off the ground and to move forward. But how do you steer? How does a pilot actually fly the thing? Well, it's all about control. It's a nonstop, delicate balancing act. Just picture a plane cruising at 35,000 feet, smooth as glass. In that moment, everything is in perfect equilibrium. The lift pushing up is perfectly canceling out the weight pulling down, and the thrust pushing forward is perfectly matched by the drag pulling back. Every single turn, every climb, every descent is just a pilot intentionally and temporarily unbalancing these forces. Pilots control this balance around 3 different axes. The first one is pitch. This is just tilting the nose up or down, kind of like nodding your head yes. And that's controlled by the elevator, those little flaps on the horizontal part of the tail. Next up is roll. This is the tilting of the wings, one side up, one side down, like tilting your head to your shoulder. This is what you feel when a plane banks into a turn. It's controlled by these flaps on the outer edge of the wings called ailerons, and they always work opposite each other. And finally, there's yaw. This is the nose of the plane swinging left or right, like shaking your head no. This is controlled by the rudder, which is on that big vertical fin at the back. Pilots use the rudder and the ailerons together to make turns that are smooth and coordinated, not sloppy. So when you take all these different pieces, the forces, the controls, the principles, and you put them all together, you get something pretty remarkable. You get an aerodynamic symphony. So let's just recap the whole thing. To even get off the ground, lift has to be stronger than weight. To move forward, thrust has to be stronger than drag. The pilot acts like a conductor, using the control surfaces to manage pitch, roll, and yaw. And flight itself is just this continuous, beautiful, dynamic dance between all 4 of these forces. So you see, it really isn't magic at all. It's just an incredibly elegant, powerful symphony of physics. It's an amazing testament to human ingenuity that we figured out how to conduct this symphony so perfectly every single day. And it kind of makes you wonder, now that we've mastered these forces to build the planes we have today, what's the next great challenge? What's the next frontier in flight going to be?